Hi, my name is Nima Saberi, and I will be presenting with my partners Luke Lindholm, Christopher Madden, Liam Sutherland on our project about concussion sensing in high-impact sports.
First, I'm going to be going over the outline of our presentation. This includes the background about traumatic brain injuries and their role in sports, then the project strategy and how we came up with our design objectives and constraints, then the design process and where we talk about all of our different designs and our data collection methods, and finally our future improvements and the economic and societal impact of our device. First, I will be going over the background related to traumatic brain injuries. Traumatic brain injuries, or TBIs, are caused by a hit to the body or head, resulting in the head and brain to move back very quickly. This movement can make the brain bounce or twist inside the skull, causing the creation of chemical changes in the brain, which can cause brain cells to be stretched or damaged, and is especially dangerous when sustained multiple times. In the video, an NFL player is knocked unconscious and receives a concussion. However, he later returned to the game due to poor concussion diagnosis. This player never played another NFL game due to concussion-related injuries. Next, I'll go over some background regarding to impact sensing devices. Recently, there has been an increase of awareness in concussions and CTE, a neurodegenerative disease caused by concussions, with stories coming out about ex-NFL players with dementia and violent behavior because of CTE. Currently, there are multiple companies developing sensors to measure impact and diagnose concussions, but studies have shown that they have very large error rates. Video analysis is also used to determine concussions, but live data readings cannot be done, so players are not protected enough from re-entering the game.
Now we're going to take you through our project strategy.
The current project problem is that the market lacks low-cost impact sensors that are able to give feedback with a high degree of confidence. Our team is trying to create a device that can sense brain accelerations and rotation accurately while still being low cost.
To solve this problem, our team has outlined 3 key design objectives. They are quality features, convenience features, and cost components. Some quality features include low error rates, quick diagnoses, and low weight and size. A few convenience features are comfortability and ease of use, and easily viewable and interpretable results. And finally, some cost components are price of the parts and peripherals, and what training for such a device would look like.
So for our design process, our original design idea started off with brainstorming what the best type of device to capture live impact data would be. So looking at the Biometrics Prevent mouthguard, which uses a custom circuit board with small accelerometers and gyroscopes. The circuit board wraps around the entire front of the mouthguard. We also looked at the I1 Biometrics Vector mouthguard, which holds the sensor in an extending part protruding from the front of the mouthguard. These both influenced our mouthguard design. So we started drafting it in CAD and SolidWorks, but as you can see by the red rectangle, the Arduino board we were using was over 60 millimeters long. So relative to the mouthguard itself, that's about the width of the mouthguard. And this wasn't the only problem we ran into. There were other questions that came up. For instance, where would be the best place to put accelerometers, gyroscopes, battery, and wiring? So this approach was too complex considering the amount of time we needed to dedicate to testing to see if the device works. And since there was no feasible way to accomplish a working flexible circuit board like the Prevent mouthguard and minimal space for our components to fit adequately like the Vector mouthguard, we decided to elect the idea of headwear or skull cap to have a stitched-in sensor at the top of the head. To show why we decided on the skull cap design, we compared it to the Prevent mouthguard, Vector mouthguard, and our mouthguard prototype on a needs analysis chart. The categories in this needs analysis chart include quality features, convenience features, and cost components. Each device has an importance and satisfaction rating, which determines the total score for that category. The total customer value is calculated by multiplying quality features rating with convenience features rating and dividing it by the cost components rating. The total scores for each category are as follows. In quality features, total score is a 96 for the skull cap prototype. In convenience features, the total score is 77. In cost components, the total score is 35, which brings our skull cap prototype's total score to be the highest on the needs analysis chart at a total of 211. So to give you more detail about this concept we came up with for a skull cap prototype, we are using the Vernier sensor GoDirect accelerometers and gyroscope. The sensor can effectively obtain a rate of 1000 Hz on each channel, and the channels we are using include the XYZ accelerometer and gyroscope channels. The good thing about the sensor is it has a Bluetooth connection and can read live data, as well as a chargeable battery with a longer battery life. It uses graphical analysis 4 software to plot points and analyze incoming data from the accelerometer and gyroscope channels. And conceptually what this would be is a sensor that is stitched in the top side of the cap to accurately detect both linear and rotational acceleration from impacts.
In this section, we'll be covering testing methods and data collection. To test our device, we constructed a testing apparatus that consists of a ballistic gel head, a pendulum, and a sliding track so the two former pieces can interact. The ballistic gel head is held in place by a form-fitting case. This allows it to be attached to a slab of wood and metal that make up the sliding plate. The sensor is then mounted on the head in a few different positions for separate trials. The testing procedure is as follows. Set the desired weight on the pendulum arm. Turn on the sensor and mount it to the ballistic gel head. Mount the head to the sliding track and move it to the impact position. Assure the sensor is receiving data. Pull the pendulum arm back to the desired launch angle using a level to measure. Release the pendulum arm and stand clear. Assure data was collected and reset everything to the initial position.
Using this test procedure, our team began to collect data samples with our initial prototype. This first graph portrays the peak linear acceleration magnitudes across 100 datasets. The values for linear acceleration are reported in Gs, where 1 G is equivalent to 9.8 meters per second squared. The first 40 datasets were completed with the sensor located at the back of the head, and the next 60 datasets were completed with the sensor located at the top of the head. The team decided to experiment with different sensor locations on the head in order to see if there was a difference in reported data at these two locations. The average peak linear acceleration magnitude with the sensor located at the back of the head was approximately 26 Gs, and the average peak linear acceleration magnitudes with the sensor located at the top of the head was approximately 65 Gs. This red line shows a threshold of 52 Gs. Previous studies conducted by the HITS database and the NFL found that if a player experienced a hit causing a peak linear acceleration magnitude that exceeds or meets this threshold, then there's a 95% chance that the player will obtain a concussion. This portrays that our sensor was able to record both impacts above and below this threshold, possibly showing its potential in identifying concussive hits. Next, the team analyzed the peak angular velocity magnitudes across the 100 datasets. The values for angular velocity are reported in radians per second.
Love it.
It was not as easy to identify exactly where the sensor location changed in this graph, potentially showing that sensor location may have a lesser influence on angular velocity than it did with linear acceleration. The average peak angular velocity magnitude with a sensor located at the back of the head was approximately 28 radians per second, and the average peak angular velocity magnitude with a sensor located at the top of the head was approximately 34 radians per second. This red line shows a threshold of 33 radians per second. Previous studies conducted by the HITS database and NFL found that if a player experienced a hit causing a peak angular velocity magnitude that exceeds or meets this threshold, then there's a 90% chance that the player will obtain a concussion. This shows that our sensor could measure values both below and above this concussive threshold. Overall, more datasets would be necessary to make a concrete conclusion on how sensor location affects angular velocity. Here is a table that summarizes our data. In total, the team collected 100 datasets averaging a peak linear magnitude of approximately 49 Gs and an average peak angular velocity magnitude of 31 radians per second. Using these datasets, the team performed a statistical analysis in order to see how similar or different the two datasets were. The t-statistic comparing linear acceleration data across sensor location was 16.5, and the t-statistic comparing angular velocity data was 4.5. This shows that sensor location affects linear acceleration values more than it does angular velocity values. Also, a two-tailed t-test was performed, and the two-tailed p-value was less than the t-critical value for both locations, portraying that we can reject the null hypothesis that there was differences in the means of linear acceleration and angular velocity across sensor locations. Our prototype was able to detect impacts ranging from approximately 2 Gs to 98 Gs, with angular velocity values ranging from 4 to 48 radians per second. Previous studies have found concussive impacts to obtain peak linear acceleration values of 52 Gs, with peak angular velocity values equal to approximately 34 radians per second. This portrays the potential for our prototype, but more testing would need to be completed in order to further prove its efficacy.
The team evaluated the final device prototype with design verification and validation based on the original needs analysis regarding functionality, safety, price, comfort, usability, and etc. The team also ensured ASTM, IEEE, FCC standards were met. Regarding the economics, this device could accrue an annual savings of $1.5 billion for college and $19.2 billion for high school in a concussion-related medical bills. This device provides important societal and ethical influence by decreasing the chance of second impact syndrome while being a potential brain injury saving device. The device can increase quality of life for impact sports athletes, youth, and professional. And currently the device is similar to current clothing sensor devices already on the market, so it will be able to be manufactured similarly.
The team dealt with numerous limitations during the course of the project. First, the ballistic gel head constantly needed repair due to the force of pendulum and mounting procedure. The consistency of testing started to be in question due to the pendulum wear and tear from numerous uses from our group and multiple other MQP groups. Finally, suspended access from on-campus resources from COVID-19 meant that no new experiments were able to be performed. For the future development of the project in general, we want to create a compatible application for trainers, and this includes accessibility to medical resources within the application, as well as being compatible with all devices, and allows data to be captured on the player history and be able to be stored within the application so trainers can use this in combination with the device, as well as to develop new testing methods to further validate our data.
Finally, we'd like to thank a few people that we wouldn't have finished this project without. First, our advisor Songbai Ji and co-advisor Haichang Zhang, as well as Lisa Wall and Fiona Levy, Meredith Merchant, and the WPI sports equipment staff.